Welcome to Relax Story, a peaceful place where gentle stories help you leave behind the worries of the day and drift into a calm, restful sleep. Each soothing narration is designed to relax your mind, ease tension, and bring a sense of comfort and peace. If you enjoy listening, please like and subscribe, and feel free to share your thoughts or story suggestions in the comments. Now, close your eyes, take a slow, deep breath, and let Relax Story guide you into a night of deep and peaceful sleep. If the entire history of life on Earth were gathered into a book millions of pages long, there would be chapters where, upon opening them, you would find that almost everything that had existed before suddenly vanished. Not just a few characters erased from the story, not just a single landscape transformed. An entire world once crowded with life became astonishingly empty. What happened during those moments? What could drive a planet overflowing with living creatures so close to silence? More importantly, how did life manage to endure and continue writing the chapters that followed? The central character here is not the crocodile, the shark, or any of the creatures we will encounter later. The protagonist is Earth's entire biosphere. Over the more than 500 million years since complex life first flourished in the ancient oceans, this planet has not followed a smooth and uninterrupted path. Its history resembles a long epic repeatedly broken by immense voids. There were times when even the most stable ecosystems seemed pushed to the brink of collapse. When we look at today's forests, grasslands, coral reefs, and oceans, it is easy to feel as though we are observing a complete world. The reality is different. The modern natural world is what remains after countless planetary-scale restructurings. Every organism alive today carries traces of crises that unfolded long before human beings ever appeared. Extinction itself is not unusual. In nature, species are constantly emerging and disappearing. Some fail in competition. Some cannot adapt to changing environments. Some simply reach the end of their evolutionary journey. These events happen quietly and rarely alter the larger picture of life. A mass extinction is something entirely different. It is a moment when an enormous proportion of species disappear within a geologically brief span of time. Ecosystems across the planet are affected simultaneously. Food webs unravel. Entire groups of organisms that once dominated the world may collapse or nearly vanish altogether. During such moments, it is not only species that become victims. The ecosystems themselves become victims. What is remarkable is that Earth has experienced events like these more than once. Around 445 to 444 million years ago, most life was still concentrated in shallow seas. Then the global climate suddenly cooled. Ice sheets expanded rapidly across vast regions of the planet. Water became locked away in ice, causing sea levels to fall. The shallow marine habitats that had once supported countless organisms gradually disappeared. That crisis wiped out roughly 85% of all species alive at the time. It was one of the first truly devastating biological shocks the planet ever experienced. But that was only the first time. Tens of millions of years later, the world entered another chapter. Ancient coral reefs flourished. Diversity in the oceans reached extraordinary levels. On the surface, everything seemed prosperous, yet beneath the water, many seas were slowly losing oxygen. Long-running environmental crises quietly weakened ecosystems from within. Between 70 and 80% of species disappeared during this extended series of events. The richness that had once made the oceans vibrant became a distant memory. What happened next was even greater. Around 252 million years ago, Earth entered the most severe biological crisis in the entire history of life. Nearly every ecosystem on the planet was affected. The rules that had governed the world for millions of years began to break apart. The upheaval was so immense that it will become the focus of the next stage of our journey. About 50 million years later, another major extinction swept across the planet. Roughly 76% of marine and terrestrial species disappeared. Many ancient reptile groups that had once played important roles in their ecosystems were eliminated. Vast ecological vacancies emerged. From those empty spaces, a new group of organisms began to rise into dominance. It was the age of the dinosaurs, yet the most famous extinction was still ahead. Around 66 million years ago, in what is now the Yucatan Peninsula, a massive celestial body between 10 and 15 kilometers wide slammed into Earth. The impact released more energy than any natural disaster humanity has ever witnessed. Dust and debris were blasted into the atmosphere, darkening the skies for an extended period. Global food chains were disrupted. Roughly 75 to 80% of species disappeared. The non-avian dinosaurs, which had ruled the planet for tens of millions of years, reached the end of their long journey. But even that is not the most astonishing part. In every mass extinction, predators die. Prey die as well. The strongest species disappear. Weaker ones are not guaranteed safety either. Advantages that brought success for millions of years can become meaningless in a remarkably short time. The familiar rules of the world suddenly stop working. What truly amazes us is not that life repeatedly stood at the edge of catastrophe. It is that after every catastrophe, life returned. New forests emerged. Oceans filled once more with living creatures. New evolutionary lineages were written from the remnants of the old world. The history of life is not really the story of the winners. It is the story of those who remained after every victory had been erased. Among the 5 great mass extinctions, one stands far above all the others. A moment when nearly the entire planet approached the brink. A moment when life itself seemed to be holding on to its final breath. Paleontologists call it the Great Dying. Before we begin, imagine a planet at the height of its biological diversity. Forests stretch across vast, dry landscapes. Shallow seas shimmer with life, crowded with countless species woven into ecosystems built through millions of years of evolution. Early mammal-like creatures are expanding their presence. Ancient reptilian lineages have adapted to a wide range of environments, from arid interiors to coastal regions. Everything appears to be operating according to the familiar rules of nature. This was Earth around 252 million years ago, during the final days of the Permian period. At that time, most of the planet's land was joined together into a single immense supercontinent known as Pangaea. Viewed from above, the world was no longer divided into the continents we recognize today. Mountain ranges, plains, and deserts flowed into one another across a landscape that seemed almost endless. Ecosystems had enjoyed ample time to stabilize. Food webs had been established for ages. Life appeared to be standing on a foundation built over tens of millions of years. What makes this story remarkable is that there were almost no obvious signs of what was about to happen. No asteroid was racing toward Earth from space. No ocean was suddenly evaporating. No warning was written across the sky. The world looked prosperous, yet far to the north of that vast supercontinent, deep beneath the planet's crust, a silent process had already begun. The ground started to split apart. Molten rock surged upward from Earth's interior on a scale far beyond anything humanity has ever witnessed from a volcanic eruption. The region that is now Siberia slowly became the center of a geological event of unimaginable magnitude. This did not unfold over hours or days. It stretched across spans of time so long that no individual organism could have realized it was living through a catastrophe. Layer after layer of lava spread across the land. One layer buried another. Immense basalt plains gradually formed, covering areas as large as multiple modern nations combined. Each eruption was only a small piece of a chain of events that continued for hundreds of thousands of years and then continued still further. But the lava was not the greatest danger. What truly changed the history of life was something invisible. Carbon dioxide poured continuously into the atmosphere. Methane escaped from deep underground. Sulfur dioxide and numerous other gases began to accumulate. Over an immense span of time, the planet's atmosphere was slowly transformed. At first, the changes may have been difficult to notice. Then, temperatures began to rise. Greenhouse gases continued to build up. More and more heat became trapped. In what was a relatively brief interval on the geological timescale, global average temperatures climbed to astonishing levels. Regions that had long enjoyed stable climates became increasingly harsh. The oceans were not spared. Seawater absorbed much of the excess heat. Vast stretches of ocean grew warmer. Ocean currents that had once carried heat and nutrients around the globe began to shift. Systems that had remained balanced for millions of years slowly lost their stability. As water temperatures rose, another problem emerged. Warm water holds less oxygen than cold water. Oxygen levels in many parts of the oceans fell to dangerous lows. Areas that had once been centers of life gradually became oxygen-poor waters. Creatures living on the seafloor were among the first victims. Many could not move away from the new conditions. They disappeared, and their disappearance triggered a chain reaction. As bottom-dwelling organisms declined, the species that depended on them also began to struggle. Links higher up in the food web started to vanish. Layer after layer of life was pulled downward together, like a building collapsing after losing its foundation. Once the food chain is severed at its roots, strength loses much of its meaning. Under normal conditions, predators hold an advantage. Species well adapted to their environment hold an advantage. Groups that dominate ecosystems hold an advantage, but these were no longer normal conditions. The prey disappeared, the predators followed. Food sources dwindled, habitats changed too quickly. Lineages that had endured for tens of millions of years suddenly became fragile. Ecosystems that had seemed almost eternal collapsed within a geological instant. The true scale of the disaster slowly emerged. In the oceans, nearly the entire familiar world was swept away. roughly 90 to 95% of marine species disappeared. On land, around 70% of vertebrate species vanished. Even insects, a group famous for its adaptability and enormous abundance, suffered severe losses on a global scale. If it were possible to stand on Earth during that era and watch across thousands of years, the landscape would seem unimaginably empty. Forests that once stretched to the horizon were no longer intact. Seas that had once teemed with life fell silent. Many of the lineages that had dominated the planet simply vanished from history. No descendants remained in the world that emerged after the catastrophe. Because of its unprecedented devastation, this event came to be known as the Great Dying. It was not merely an extinction. It was the moment when life came closer to failure than at any other point in its history. Yet the strangest part is not what was lost. The strangest part is what remained. Almost every path to survival had been closed. Almost every ecosystem had been destroyed. Almost every familiar rule that once helped species thrive had stopped working. But not all of them. A handful of lineages endured. Very few. Very fragile. Easy to overlook amid the ruins of the old world. The history of life is not always written by the victors. There are moments when the most astonishing achievement is not growth, expansion, or dominance. The most astonishing achievement is simply continuing to exist. There are periods when life does not win. It merely survives long enough to wait for the world to begin again. In that post-apocalyptic world, a few ancient lineages were still present. They were not the fastest creatures. They were not the strongest. They were not the rulers of the planet. One of them still lies quietly beside the water's edge today. Its story began more than 200 million years ago, while much of the world around it was disappearing. What allows a lineage of animals to survive the catastrophe that brought the age of dinosaurs to an end? At first glance, that question seems to point toward giant creatures, the most fearsome predators, or the most advanced evolutionary success stories in history. Yet when we look across the still surface of a tropical swamp, the answer is lying quietly in plain sight. Only a pair of eyes rises above the water. Only a dark back nearly disappears into the mud and reeds. A body that appears to have changed little over tens of millions of years watches the world in silence. The ancestors of modern crocodiles first appeared during the late Triassic period, more than 230 million years ago. At that time, the earliest dinosaurs were only beginning to step onto the stage of history. While dinosaur lineages gradually expanded their influence across the land, another evolutionary branch quietly began its own journey along rivers, lakes, marshes, and estuaries stretching across the ancient continents. Looking at a crocodile today, it is easy to imagine that its ancestors always looked much the same. The reality is far more complex. Over hundreds of millions of years, crocodile relatives experimented with an astonishing range of lifestyles. Some species ran on two legs with remarkable speed. Others lived entirely on land. Some carried long legs and slender bodies, chasing prey across open ground in a way that resembled fast-running animals more than ambush hunters lurking in muddy water. The group was once so diverse that its members occupied almost every corner of the Mesozoic world. They lived alongside dinosaurs for most of that era. They witnessed the rise of enormous plant eaters, They saw giant predators dominate the land. They endured while ancient forests covered vast regions of the planet. But time eventually posed a far more difficult challenge than any ecological competition. If the crocodile family was once so diverse, why did most of its ancient branches disappear, while only a handful survived into the present day? About 66 million years ago, the greatest test in the history of life began. A massive asteroid slammed into what is now the Yucatan Peninsula. The energy released in that moment exceeded anything humanity has ever witnessed. Dust, ash, and vaporized material were hurled into the atmosphere. Sunlight faded, temperatures fluctuated, plants died on a massive scale. Food chains on land began to collapse from the ground up. Creatures that had ruled the world for tens of millions of years could not survive this period. Non-avian dinosaurs vanished. Many groups of large reptiles followed the same path. Numerous apex predators that once stood at the top of every food chain never appeared again in the fossil record. Yet somewhere within murky waters, certain crocodilian groups endured. They crossed the extinction boundary. They entered a new world. They continued to breed, hunt, and survive all the way to the present day. What made them different? The first answer is not found in their jaws lined with sharp teeth, not in their muscular strength, not in their hunting ability. The secret lies in something far less noticeable. It lies in the pace at which they live. Crocodiles are cold-blooded animals. They do not need to burn energy constantly to maintain a stable body temperature the way mammals do. As a result, their energy requirements are significantly lower than those of many animals of similar size. During stable times, this difference may not seem especially important, but when food becomes scarce, when each passing day grows harder than the one before, that advantage becomes incredibly valuable. Species that require large amounts of energy are often among the first to come under pressure. They must keep searching for food simply to stay alive. Crocodiles do not live by that rhythm. They can remain motionless for hours, for days, expending very little energy on unnecessary activity. A body that runs more slowly can endure much longer when the world becomes a place of scarcity. Yet conserving energy is only half the story. An even more remarkable ability lies in the art of waiting. After a large meal, an adult crocodile can survive for weeks, sometimes even months, depending on environmental conditions. In ordinary times, this is simply a biological trait. During a planetary crisis, it becomes an invaluable survival tool. Many predators must constantly move in search of opportunity. Crocodiles do not. They can wait in the water, wait along a riverbank, wait among the reeds, wait until a rare opportunity finally appears. Many creatures survive because they can run faster than their rivals. Crocodiles survive because they do not need to run at all. Still, the ability to wait would mean little if there were nowhere stable enough to endure. Fortunately for their ancestors, rivers, lakes, marshes, and inland waterways acted as natural refuges during the chaos. While many terrestrial ecosystems suffered catastrophic collapse, freshwater environments retained part of their living foundation. Small fish survived. Aquatic organisms continued to reproduce. Floating carcasses became an additional food source for opportunistic survivors. These waters were like islands of survival in a changing world. They were not perfect. They were not completely safe. but they were stable enough for certain crocodilian lineages to make it through the most difficult chapter in the history of life. Even so, one final factor remained, perhaps the most important of all. Crocodiles are not particularly picky. They eat fish, they eat birds, they eat small mammals, they eat carrion. They take advantage of almost any opportunity that comes their way. They do not depend entirely on a single source of prey. When one food source disappears, they still have the ability to turn to another. This marks an important difference between thriving in stable times and surviving through a crisis. Many species succeed because they become highly specialized. They perform one role with extraordinary efficiency. But when the environment changes suddenly, that very perfection can become a burden. Crocodiles are not the fastest creatures, not the smartest, nor the quickest to change. They are simply flexible enough to keep going when familiar conditions disappear. Looking back across a journey that stretches more than 230 million years, a pattern slowly emerges. Survival does not always belong to the strongest species. Sometimes it belongs to the species that spends the least, waits the longest, and depends the least on perfect conditions. There are periods in the history of life when speed brings victory. There are moments when strength determines status. But when the world begins to fall apart, endurance often travels farther than superiority. The crocodile is the first living proof of that rule. And yet, it was not the first creature to follow it. Long before the earliest crocodile ancestors appeared, another animal was already crawling across ancient tidal flats. It watched oceans change shape. It watched continents drift apart and collide again. Within its body flows a very unusual kind of blue blood, a creature that has survived for nearly 500 million years. What would a creature look like if its ancestors had appeared before the first forests ever grew on land? It is a difficult question to picture, because when we look at the world today, almost everything familiar belongs to a very different planet. Forests stretch from the tropics to the temperate zones. Birds cross the skies. Mammals occupy countless habitats. Humans build cities along coastlines and rivers. Yet there was a time when none of these things existed. Around 450 million years ago, during the Ordovician period, most life was still concentrated in the oceans. Dinosaurs had not yet appeared. Birds did not exist. Mammals had not stepped onto the evolutionary stage. Modern forests were still far in the future. Even land-dwelling vertebrates had not yet become a force shaping the planet. In that unfamiliar world, the lineage of the horseshoe crab began its journey. What makes that journey remarkable is not that it lasted a few million years or even a few tens of millions of years. It lasted nearly 500 million years. If you stand on a beach today and watch a horseshoe crab slowly moving across wet sand, it feels as though you are looking at a surviving fragment of an earth so ancient that it is almost impossible to imagine. Its basic form remains instantly recognizable. A broad, curved shell like an ancient shield, a long-tailed spine resembling a slender sword, a pair of compound eyes positioned at the front of the body, like observation devices from another age. Today, the horseshoe crab belongs to a lineage represented by only 4 surviving species. They are found along the eastern coast of North America, around the Gulf of Mexico, in parts of Southeast Asia, and in the waters surrounding Japan. Although their name leads many people to associate them with modern crabs, they are not true crabs at all. Their closer relatives are spiders, scorpions, and other members of the chelicerate group. That discovery completely changes how we view this animal. The creature crawling across the tidal flats is not a primitive crab. It is one of the last living representatives of an ancient lineage that has traveled through multiple geological ages. But surviving for a long time does not mean standing still in the face of change. A larger question begins to emerge. How can a lineage endure for so long while countless others vanish from history? Soon after the ancestors of horseshoe crabs appeared, the planet entered one of its earliest biological crises. At the end of the Ordovician period, major climate shifts caused severe damage to marine ecosystems. Many groups of organisms never fully recovered. The horseshoe crab lineage continued on. Tens of millions of years later, new upheavals arrived during the Devonian. Marine ecosystems once again suffered widespread collapse. Connections that had remained stable for millions of years were broken apart. They were still there. Then, around 252 million years ago, the planet experienced what is widely regarded as the most devastating mass extinction in the entire history of life. Most marine species disappeared. Large regions of the ocean became oxygen poor. Ecosystems were so heavily damaged that they almost seemed forced to begin again from scratch. The horseshoe crab lineage survived that as well. Then came the end Triassic extinction. After that came the asteroid impact that ended the Cretaceous period, when the skies darkened, global food chains fractured, and the non-avian dinosaurs disappeared from the world. The horseshoe crab emerged on the other side of that disaster too. Many famous species in evolutionary history lasted only a few million years before being replaced or driven to extinction. Meanwhile, this lineage has witnessed entirely different biological worlds rise and fall one after another. It has lived through more ages than humans can easily comprehend. The first secret behind that survival is not strength. It is simplicity. Along the seafloor and across tidal flats, horseshoe crabs feed on small organisms living within the sediment. Marine worms, tiny mollusks, and various bottom-dwelling creatures become their regular food sources. It is not a glamorous hunting strategy. There is no explosive speed, no venom, no sophisticated ambush techniques. They simply make use of what is available. That simplicity creates a unique advantage. They do not depend on a single prey species. They are not tied to a complicated food web. They do not require highly specialized environments in order to survive. When the world is stable, sophisticated strategies often bring great rewards. When the world becomes chaotic, creatures that require fewer special conditions often stand a better chance of surviving. Yet simplicity alone is not enough. A creature that survives for hundreds of millions of years must also become familiar with change. Horseshoe crabs do not live in perfectly stable environments. They inhabit coastlines, estuaries, brackish waters, and tidal flats that are constantly shaped by tides, weather, and seasonal cycles. There, salinity is never fixed, temperature is never fixed, water levels are never fixed. Every day becomes a small test of adaptability. Creatures accustomed to living in changing environments often develop a greater ability to withstand major disruptions. They do not expect the world to remain the same. They are already familiar with the fact that it changes. By contrast, Many species that thrive in highly stable conditions become vulnerable when those conditions suddenly reverse. In Earth's turbulent history, that is no small advantage. But there is another secret that makes the horseshoe crab remarkable even in the age of humans. That secret flows through its body. The blood of a horseshoe crab transports oxygen differently from the way human blood does. Instead of using iron-based hemoglobin, it relies on copper-based hemocyanin. That characteristic gives its blood a distinctive blue color. That alone would be strange enough. Yet the truly remarkable feature lies in its ancient immune system. The immune cells in horseshoe crab blood react with extraordinary sensitivity to certain toxins produced by bacteria. Even extremely small amounts can trigger a detection response. That ability has become an invaluable tool in modern medicine. Compounds derived from horseshoe crab blood have been used to test the safety of vaccines, injectable drugs, medical devices, and many other biological products. Before some products ever come into contact with the human body, they undergo rigorous testing procedures in which traces of this ancient creature still play a role behind the scenes. There is something deeply remarkable about that image. A creature whose journey began before forests existed on land. A creature that survived repeated moments when the world nearly collapsed. A creature with blue blood that now helps protect the health of millions of people in the 21st century. Some organisms are like silent witnesses to history. They do not build vast biological empires. They do not dominate the planet. They do not redirect the course of life through dramatic displays of power. They simply continue to exist. And sometimes, that is even more astonishing than domination. The story of the horseshoe crab reveals an important principle. Long-term survival does not necessarily require becoming stronger, larger, or more complex. There are times when the ability to remain stable in a constantly changing world becomes the most powerful evolutionary strategy of all. If the horseshoe crab survived by changing very little, the next character in our story followed an almost opposite path. It has continuously reinvented itself through time. It has appeared again and again in new forms. For more than 400 million years, the oceans have never been completely without it. That is the story of the shark. How many times does a group of animals have to reinvent itself to survive for more than 400 million years? The question sounds simple enough until we begin pulling time backward to the oldest oceans where vertebrate life was just beginning to expand. Between roughly 450 and 420 million years ago, Earth was a world that would be almost impossible to recognize today. No dinosaurs walked across the land. No flocks of birds crossed the skies. No mammals wandered through forests. Complex life still belonged largely to the water. Across the shallow seas that stretched around the planet, the earliest members of the shark lineage appeared. They were not the terrifying killing machines that modern people often imagine. They were small, unassuming creatures, just one part of the crowded communities that filled the ancient oceans. Around them swam giant armored fish protected by heavy bony plates. Creatures that dominated the seas for immense spans of time. Looking at a great white shark or a tiger shark today, it is easy to assume that sharks have always occupied the top of the hierarchy. Yet at the beginning of their story, their distant ancestors held no such position. They were merely small shadows, experimenting with their first ways of surviving in a fiercely competitive world. What makes the story fascinating is that those ancient animals look nothing like the familiar image of a shark today. Around 370 million years ago, one of the best-known early representatives appeared. It is known as Cladocelache. With its streamlined body and swift movements through the water, it already carried hints of the shape we associate with modern sharks. Yet its mouth sat at the front of its head rather than underneath it, as it does in most sharks today. It was a design from a different stage of evolutionary experimentation, when this lineage was still searching for the most effective structures for a predatory life. Then came Stethocanthus, an even stranger creature. Rising from its back was a remarkable structure resembling a giant brush or an anvil positioned just behind the head. Some researchers believe it may have played a role in species recognition or mating displays. Although its exact purpose remains uncertain, its existence reveals how much more diverse ancient sharks once were than we usually imagine. And then there was Helicoprion, one of the most bizarre animals ever to emerge from the history of cartilaginous fish. Instead of the familiar rows of teeth, it possessed a spiral tooth whorl that looked like a circular saw blade. For decades, scientists did not even know where that structure belonged. Some thought it sat on the nose. Others believed it was attached to the back. Only with modern imaging technology were researchers finally able to determine that the strange spiral actually occupied the lower jaw. Looking at Cladocelache, Stethocanthus, and Helicoprion, a question naturally begins to emerge. If sharks are among the great survivors of life's history, why have almost all of these ancient sharks vanished? The answer lies in a very common misunderstanding. People often say that sharks have existed for more than 400 million years, as if they are talking about a single species. The reality is entirely different. No shark species alive today has persisted unchanged from that distant time. Those earliest forms disappeared long ago. What survived was not a species. What survived was an evolutionary lineage. Every time the world changed, that lineage reappeared in new forms. After the crises at the end of the Devonian period, many groups of armored fish that once dominated the oceans disappeared. Ecological space opened up. The surviving shark lineages began diversifying more rapidly, experimenting with new hunting strategies and new body plans. Then came the Permian mass extinction, the greatest biological catastrophe in Earth's history. Countless organisms vanished. Many ancient shark lineages disappeared as well, yet some survived. They continued evolving in entirely new directions, producing descendants that no longer resembled their ancestors. Hundreds of millions of years later, the asteroid at the end of the Cretaceous once again transformed the oceans. Marine ecosystems were reorganized. Food sources shifted. Entire groups of organisms disappeared. Once again, sharks adjusted themselves to fit a new world. The pattern repeated so many times that a rule slowly emerged. Whenever the world changed, some sharks vanished. Yet the shark lineage itself never disappeared completely. Behind that persistence lies a remarkably effective evolutionary toolkit. One of its greatest advantages begins with the skeleton itself. Unlike most familiar vertebrates, sharks do not rely on skeletons made primarily of hard bone. Their framework is composed largely of cartilage, This structure is lighter, more flexible, and highly efficient for movement through water. A lighter body means less energy spent traveling across vast distances of ocean. But speed and flexibility are only part of the story. Hidden within the shark's head are specialized organs capable of detecting electricity. They can sense tiny electrical signals generated by the muscles and nervous systems of other animals. In murky water, in the darkness of night, or beneath layers of sand on the seafloor, those faint signals still stand out like invisible guideposts. A shark can locate prey even when its eyes are nearly useless. An even stranger adaptation lies within its jaws. Humans have only 2 sets of teeth during a lifetime. Many animals are similarly limited. Sharks are different. Behind every row of teeth waits another row ready to move forward. When a tooth breaks or falls out, another takes its place. The process continues throughout the animal's life. In some species, the total number of replacement teeth may reach tens of thousands. That endless renewal feels almost like a reminder that long-term survival sometimes requires continually replacing what has become outdated. There is another factor quietly contributing to the success of this lineage. Not all sharks feed on the same things. Some hunt fish, some hunt squid, some attack large marine animals, some scavenge. Others survive by filtering plankton from seawater. This diversity prevents the entire lineage from depending on a single resource. When ecosystems change, at least some groups still have a chance to adapt. That flexibility has produced some astonishing exceptions. In the cold waters of the North Atlantic lives the Greenland shark. Many individuals can survive for more than 2.5 centuries. While many predators live according to the fast rhythms of a few decades, this animal seems to move according to the time scale of multiple human generations. A young Greenland shark may be born while an empire still exists and continue swimming long after the world has entered an entirely different era. At the opposite extreme is the whale shark, the largest fish alive on Earth. A body longer than a city bus creates the impression of a formidable giant. Yet it does not hunt large prey. Its enormous mouth is used primarily to filter tiny plankton drifting through the water. It is remarkable that century-old Greenland sharks, gentle plankton-eating whale sharks, and apex predators like the great white shark all belong to the same evolutionary family. That fact reveals the most important secret of this entire journey. Sharks did not defeat mass extinctions. Many times, they were victims of them as well. Numerous highly successful lineages vanished forever. The difference is that this lineage never stopped experimenting. It never stopped changing. It never stopped producing new forms capable of facing a new world. Its persistence did not come from remaining the same. In many cases, it came from accepting that the old form no longer worked. The things that endure the longest in the history of life are rarely the most unchanging. They are the ones willing to change when circumstances demand it. Beyond the oceans, another creature was preparing for change in a far stranger way. It did not place its entire future in the water. Long before many animals even considered leaving aquatic environments behind, this creature quietly carried a backup plan for droughts and disappearing waterways: a lung. What happens if the only place you can live suddenly disappears for months at a time? If the familiar lake becomes nothing more than cracked mud beneath a burning sun? If the water that sustained you throughout your life retreats without a trace, is there any path left besides death? More than 400 million years ago, during the early years of the Devonian period, a lineage of fish appeared in an age when life beneath the water was exploding with unprecedented diversity. Ancient rivers wound their way across still untamed landscapes. Freshwater lakes stretched across low plains. Seasonal wetlands constantly shifted their shape with rainfall and temperature. It was an era in which countless new groups of fish emerged, competing for every patch of water, every shoreline, every expanding ecosystem. Amid that world appeared the lungfish. Today, descendants of this ancient lineage still survive in Africa, South America, and Australia. They are not dominant predators. They do not possess extraordinary speed or particularly striking appearances. At first glance, a lungfish seems like an ordinary fish, quietly inhabiting waters that few people notice. Yet inside its body lies one of evolution's most unusual decisions. While most fish became increasingly tied to the water around them, lungfish seem to have retained a lingering doubt. They behave almost as if their environment can never be fully trusted, as though somewhere deep within an ancient evolutionary memory. This lineage has always prepared for the possibility that water might betray it at any moment. The secret is not found in its fins, not in its muscles, not in its swimming ability. It lies deep inside its body. Many Devonian lakes were far less stable than they appeared. As temperatures rose, oxygen levels dissolved in the water began to fall. Some lakes became enormous traps. The water remained, but its ability to support life slowly faded away. For most fish, this was a serious crisis. They depended entirely on their gills to extract oxygen from the water. When oxygen dropped below critical levels, life itself began to suffocate. The lungfish responded differently. As the water became increasingly stagnant, it slowly rose toward the surface. Its mouth broke through the thin boundary between water and air. Then it took a breath, because alongside its gills, the lungfish carries a remarkable respiratory organ. Inside its body are highly vascularized air sacs connected to the digestive tract, functioning in a way strikingly similar to the primitive lungs that would later appear in land-dwelling vertebrates. In moments of crisis, it simply switches from one respiratory system to another. While other fish struggle with oxygen deprivation, the lungfish merely changes how it acquires oxygen. What makes this so astonishing is that it was not an emergency invention. It was not a temporary solution for one particularly harsh drought. It was a backup plan prepared hundreds of millions of years in advance, a system already built for the day when the environment no longer behaved as expected. Yet the ability to breathe air is only part of the story. Something even stranger happens when it is not only oxygen that disappears, but the lake itself. Across many parts of Africa today, seasonal lakes can dry out completely during prolonged dry seasons. What was once an open body of water gradually shrinks into isolated pools. Those pools become patches of mud. Eventually, only cracked earth remains beneath the sun. For most fish, this is the end. But some species of lungfish perform something that seems almost impossible. As the water retreats, they burrow deep into the mud below. Their bodies begin secreting mucus that envelops them completely. Over time, this mucus hardens into a protective cocoon surrounding the animal. From the outside, it is as though the creature has vanished from the world. Yet profound changes are taking place beneath the mud. Its heartbeat slows. Its breathing falls to a minimum. Its metabolism drops dramatically. The body enters an extreme state of energy conservation, as if trying to stretch every remaining moment of existence. It does not attempt to defeat the drought. It waits for the drought to end. Months pass. Sometimes the harsh conditions last far longer, yet the lungfish remains alive within its cocoon. Then the rains return. The ground softens. Water slowly fills the old lake beds once more, and the creature that seemed lost to the world awakens. It emerges from the mud. It swims away. It resumes its life. As though the long interruption had been nothing more than a dream, many organisms try to escape disaster. The lungfish chose a different strategy. It became part of the disaster itself and quietly waited until the world recovered. Yet the significance of lungfish reaches far beyond their ability to survive drought. Around 375 million years ago, a group of lobe-finned fish inhabited ancient shallow waters. One of the most famous representatives of this period was Tiktaalik. It was not a lungfish. However, it belonged to a branch of life closely related to the path that eventually led to four-limbed animals. Inside creatures like these, evolution was experimenting with a bold idea. Their fins began developing new characteristics. Their bodies gradually adapted to shallow water, muddy environments, and a world where access to air was becoming increasingly important. From those experiments, carried out over millions of years, the first tetrapods eventually emerged. One day, far in the future, descendants of that branch would walk onto land, dominate continents, build forests, give rise to dinosaurs, mammals, and eventually humans. Modern lungfish are not our direct ancestors, but they are among the closest living relatives of the tetrapod lineage. Every time a lungfish rises to the surface and takes a breath of air, we are witnessing a behavior rooted astonishingly close to the era when life first began preparing for its journey beyond the oceans. It feels like a surviving fragment of memory from one of the most important moments in vertebrate history. And that leads to a larger question. What truly allows a lineage to survive through hundreds of millions of years of change? The lungfish does not answer with strength. When water is plentiful, it lives like an ordinary fish. When the water disappears, it almost falls asleep alongside time itself. When the rains return, it awakens and continues the journey where it left off. While many organisms depend entirely on environmental stability, the lungfish carries a contingency plan within its own body. It never assumes that the world will continue functioning as it always has. It prepares for the day everything changes. Perhaps one of the most effective survival strategies in the entire history of life has never been the ability to overcome every catastrophe. Sometimes the more important skill is simply remaining alive long enough for the catastrophe to end on its own. The oldest lineages are rarely the strongest. They are the ones capable of waiting longer than the disasters themselves. Some creatures survive by waiting, but another creature seems to have taken that idea even further. It moves so slowly that time itself appears to leave barely any mark upon it. While entire biological dynasties rise and disappear, it has remained almost unchanged through spans of time that are difficult to comprehend. A reptile often mistaken for a lizard, but it is not a lizard at all. What happens when an entire biological dynasty that once spread across vast regions of the planet almost completely disappears, leaving behind only a single representative still alive today? It sounds more like the premise of a novel than a real story. Yet on a scattering of small islands off the coast of New Zealand, around the cold and wind-swept waters of the Cook Strait, there is still a creature quietly carrying the memory of an ancient lineage on its back. It is called the Tuatara, a reptile so modest in appearance that it can easily go unnoticed among rocks, grasses, and coastal shrubs. Yet its history stretches back roughly 250 million years to the early days of the Triassic period. At that time, Earth had only just emerged from the greatest mass extinction ever known. Life was beginning to rebuild the world from what remained. Dinosaurs had only recently appeared as small and unremarkable animals. Mammals were barely worth noticing. Across the continents, countless groups of primitive reptiles competed for new opportunities in a recovering world. Most ancient creatures still alive today are merely small surviving branches of once larger family trees. The Tuatara is different. It is not simply the last member of a genus or a family. It is the final representative of an entire order of reptiles that once occupied multiple ancient continents. A biological dynasty that has almost completely vanished from history. The strange thing is that very few people realize this when they first see one. From a distance, a Tuatara looks remarkably similar to a lizard. Its low body, sturdy limbs, long tail, and scaly skin naturally lead many observers to place it among the familiar lizards they already know. But the resemblance exists only on the surface. Lizards and snakes belong to a different evolutionary branch. The Tuatara comes from a lineage that split away from that branch very early in reptilian history. Hundreds of millions of years ago, relatives of the Tuatara lived across regions that are now Europe, North America, South America, and Africa. They survived in an age when the continents were still joined together as giant supercontinents. Then time began its familiar work. One group after another disappeared. Their range slowly contracted. Once abundant evolutionary branches became increasingly rare. Eventually, only a single representative remained, surviving on islands off the coast of New Zealand. When we look at a Tuatara, we are not really looking at an ordinary reptile. We are looking at the final living chapter of a book whose pages have almost entirely been lost. If nearly the whole lineage vanished, what allowed this creature to endure for so long? Part of the answer lies in its unusual pace of life. The Tuatara grows extraordinarily slowly. Many reptiles complete most of their development within their first few years. A Tuatara continues growing for decades. Sexual maturity often arrives only after 10 or even 20 years of life. Its entire existence seems to unfold as though time itself is moving more slowly. Every process, from growth and reproduction to aging, takes place at an astonishing pace. Many individuals live for more than a century. Some males remain capable of successful reproduction even beyond that mark, while countless species race against time to leave behind the next generation. The Tuatara appears to live according to its own rhythm, calm and unhurried. But slow living is not its only secret. Most reptiles perform best in warm environments. Their bodies depend heavily on external temperatures. The Tuatara follows a different path. It remains active in cool conditions, with an ideal temperature range significantly lower than that of many other reptiles. This trait turned the islands of New Zealand into a natural refuge. The cold and windy coastal habitats offered little attraction to many competitors. Places where other species struggled became ideal environments for the Tuatara. Sometimes, survival does not come from winning the fiercest competition. Sometimes, it comes from thriving where few others wish to live. Then, there is the feature that made the Tuatara famous around the world. On the top of its head sits a structure often referred to as a third eye. This structure contains several components similar to those of a true eye, including light-sensitive tissues, a simple lens-like structure, and neural connections. Yet, it is not used to view the world in the way ordinary eyes do. Instead, it functions as a light-sensing organ. It helps the body detect changes in environmental light levels, contributing to hormone regulation, maintaining daily biological rhythms, and supporting seasonal reproductive cycles. In young individuals, this structure is more clearly visible on the top of the head. Over time, skin and scales gradually cover it, making it increasingly difficult to notice. It serves as a fascinating reminder that within this small reptile remain biological designs from a much older world. Mechanisms that first appeared in distant ages continue operating quietly in the modern era. By this point, the story is no longer just about the Tuatara. The dinosaurs disappeared long ago. Most members of its own lineage disappeared as well. Continents repeatedly drifted apart and collided again. Oceans changed shape. Climate shifted through countless cycles of warmth and cold. Yet on the windswept islands of New Zealand, the Tuatara continues its slow and steady life, much as it has for millions of years. When we look at this animal, we are seeing more than a reptile. We are seeing the last representative of an evolutionary branch that once cast its shadow across vast regions of the planet, a living memory of the ancient world still breathing in the present. Some creatures survive by constantly changing to keep pace with the world around them. Some survive through sheer endurance in the face of hardship. But there are also creatures that survive because they eventually find a place where the pace of change becomes slower than the distance separating them from the past. Yet ancient survivors do not exist only on isolated islands. Somewhere beyond those shores lives a fish that has been swimming through rivers since before the first dinosaurs ever appeared. A creature armored in plates that make it resemble a living fossil. Each time it quietly rises from the water, it feels as though a fragment of prehistory is rising with it. Can a fish live long enough to witness 3 generations of humans being born, growing old, and passing through life? The answer exists in vast waterways stretching from the Caspian Sea, the Black Sea, the Danube, the Volga, and the Amur, to the immense river basins of North America, in rivers that flow toward the Atlantic and Pacific across the Northern Hemisphere. A creature still occasionally appears whose presence feels less like a fish and more like a surviving fragment of Earth's ancient memory. It is the sturgeon. The ancestors of the family Archipenseridae first appeared more than 200 million years ago. That was long before humans existed, and even during the early age of the dinosaurs. The supercontinents were still slowly drifting apart. On land, the first dinosaur lineages were only beginning to expand their presence. Modern birds had not yet appeared. Mammals remained small creatures, living quietly in the shadows, within the ancient river systems of that primordial world. The earliest ancestors of sturgeon had already begun swimming through silty waters. At first glance, a sturgeon looks like something that has stepped straight out of a fossil. Even more remarkable is the fact that this impression is not entirely an illusion. Their bodies still preserve many features that have endured through hundreds of millions of years of evolutionary history. Spend a few more seconds observing one, and it becomes easy to understand why sturgeon are often called the living fossils of the rivers. Their elongated snout projects forward, giving them an appearance unlike most modern fish. Their mouth sits on the underside of the head rather than at the front. In front of that mouth hang sensory barbels that constantly sweep through murky water. Their asymmetrical tail carries the signature of ancient fish lineages. Running along the body are 5 rows of prominent bony scutes, resembling pieces of armor assembled in prehistoric times. These structures do not exist merely to create a strange appearance. The sensory barbels function as a sophisticated detection system along the riverbed, helping locate prey hidden beneath mud and sand. The downward-facing mouth allows them to vacuum up small organisms living near the bottom. The bony armor protects the body from many natural hazards. While countless groups of fish have repeatedly transformed their forms throughout evolutionary history, sturgeon have retained many ancient characteristics. They serve as a reminder that not every successful design must constantly reinvent itself. Yet their ancient appearance is not the greatest secret they carry. The real secret lies inside their bodies. Sturgeon are not sharks, yet much of their skeleton remains composed of cartilage rather than the fully ossified skeleton found in most modern bony fish. It is a surviving trace from some of the earliest chapters of fish evolution. A lighter skeleton allows for greater flexibility in the water. It also reduces the biological cost of building and maintaining bone tissue. What is remarkable is that this ancient design never became obsolete. After hundreds of millions of years of testing, it still works well enough to survive into the present day. But if the skeleton helps sturgeon move, their life strategy is what has carried them so far through time. Many sturgeon species develop at an astonishingly slow pace. They grow slowly, they mature late, they reproduce infrequently. In return, their lifespan far exceeds that of many other fish. The beluga sturgeon, the famous inhabitant of the Caspian and Black Seas, offers a striking example. Some individuals can live for more than a century. A few records even suggest lifespans exceeding 120 years. Imagine an individual born in the early years of the 20th century. During its lifetime, several generations of humans would have appeared, grown old, and disappeared. The children who once saw it might have become grandparents, or even great-grandparents, to other children. They do not survive by living fast. They survive by stretching time itself. But the life cycle of a sturgeon is not only long, it also spans multiple worlds. Much of the life of many sturgeon species unfolds in the sea. Then, when the breeding season arrives, an ancient instinct awakens. They begin their journey upstream into great rivers such as the Volga, Danube, Amur, Yangtze, and the vast river systems of North America. On the surface, it seems like a simple life cycle, viewed on a geological scale. However, it is something extraordinary. It connects the ocean to the estuary to the interior. Different environments become linked together in one continuous cycle. These migrations have repeated themselves for millions of years. They began long before any civilization appeared on this planet. Ironically, the very strategy that helped sturgeons survive Earth's greatest upheavals has become one of their weaknesses in the modern age. Hydroelectric dams built across major rivers have blocked many of the ancient migration routes. Journeys repeated through countless generations have been abruptly interrupted by concrete walls that have existed for only a brief moment in history. Pollution alters water quality, degrades spawning grounds, and affects the development of young fish. The harvest of caviar has created decades of fishing pressure, causing severe declines in many populations. As a result, most sturgeon species today face varying levels of threat. Many have moved alarmingly close to the edge of extinction. It is a paradox worth reflecting upon. A lineage that witnessed continents rearranging themselves, one that survived mass extinctions capable of erasing much of life on Earth, one that endured environmental changes unfolding across millions of years. Now it must adapt to changes occurring within only a few centuries. What once helped sturgeons survive was their slow pace of life. They evolved according to the rhythm of ancient rivers, where change usually unfolded gradually. But the modern world is moving far faster than the evolutionary tempo they have known for hundreds of millions of years. Perhaps that is what sturgeon teach us about time. Survival in the past does not guarantee survival in the future. There are creatures capable of enduring planetary transformations that unfold across millions of years. Yet even they can struggle when confronted with changes occurring within a period shorter than their own lifespan. Crocodiles, horseshoe crabs, sharks, lungfish, tuataras, sturgeon. At first glance, they seem to belong to entirely different worlds. Each possesses its own body, its own way of life, and its own path through history. But the longer we observe them, the more a pattern begins to emerge behind those differences. There is a trait that keeps appearing, a quiet rule that seems to surface again and again among nearly every long-lived survivor in the history of life on Earth. What truly connects a shark silently cutting through the deep ocean with a tuatara lying motionless among the wind-swept islands off the coast of New Zealand? What allows a lungfish buried beneath dried mud to belong in the same story as the horseshoe crab? A marine creature whose blue blood has passed across ancient shorelines older than the memory of most modern life. At first glance, they seem to have almost nothing in common. Crocodiles belong to rivers, lakes, and swamps, where still water can conceal a patient predator. Horseshoe crabs belong to tidal coastlines shaped by the rhythm of rising and falling seas. Sharks belong to the vast open ocean. Lungfish inhabit waters that may one day disappear entirely. Tuataras are the lingering shadows of an ancient reptilian branch isolated on islands. Sturgeons drift through great rivers like scaled fragments of a distant age. They emerged in different eras, belong to different evolutionary lineages, and live in worlds that barely touch one another. Some are predators, some filter feed, some wait, some hide, some endure. Yet when placed side by side, their outward differences begin to fade. revealing a quieter pattern beneath. Human intuition often assumes that the creatures that survive the longest must also be the most perfect. We naturally imagine survival as a reward reserved for those that are stronger, larger, faster, smarter, or better equipped than everything around them. But evolutionary history rarely confirms that belief. Instead, it repeatedly leaves behind a colder lesson. Creatures that become too perfectly adapted to one particular world can vanish with surprising speed when that world changes. The fastest to disappear are not always the weakest. Sometimes they are the most specialized. In a stable environment, specialization is a remarkable advantage. A species can become extraordinarily efficient by feeding on a single resource, hunting a particular type of prey, living within a specific habitat, or relying on a food chain that rarely changes. Every part of its body, every behavior, every rhythm of its existence becomes sharpened for one set of circumstances. As long as those circumstances remain, it can become a master of its world. But Earth rarely keeps the stage unchanged for very long. When climates shift, when seas rise or retreat, when oxygen levels fall, when prey disappears, when vegetation transforms, or when entire ecosystems collapse like a roof that has lost its supporting pillars, species that depend too heavily on one thing are left with few alternatives. They do not simply lose food, they lose a way of life. They do not merely lose habitat. They lose the very logic upon which their existence was built. Many ancient predators once ruled their ecosystems in exactly this way. They were powerful within worlds that seemed almost perfectly designed for their bodies and instincts. Yet when those worlds fell apart, strength alone no longer mattered. They disappeared not because individual animals failed to fight for survival, but because their entire survival strategy no longer had a place to stand. The longest lasting survivors often leave themselves more exits. Crocodiles offer a quiet but clear example. They can hunt fish beneath the surface, seize birds when the opportunity appears, ambush mammals approaching the riverbank, or feed on carrion when times become difficult. They do not build their entire existence around a single food source. Hidden within that seemingly ancient body is a highly practical strategy. When one door closes, another remains just wide enough to pass through. Sharks tell the same story on an even broader scale. It is not a single shark species that has survived through deep time, but an entire family of creatures that have found many different ways to exist. Some hunt seals, some hunt fish, some pursue squid, some feed on carcasses drifting through the sea. Others grow enormous while surviving by filtering tiny plankton from ocean water. Their success does not rest in one perfect design. It rests in the ability to expand into many different paths. The ocean changes, but not every door within the ocean closes at the same moment. When one way of life becomes vulnerable, another can continue. Food, however, is only part of the story. Habitat is an even greater test. Lungfish survive as though they have always known that lakes can betray them. When water levels fall, when pools become warm, muddy, and starved of oxygen, many fish find themselves trapped within the very environments that once sustained them. The more they struggle, the more confined they become within a shrinking world. The lungfish chooses a different path. It rises to the surface and breathes air using its primitive lungs. When drought stretches on, it burrows into the mud, folds itself inward, slows its metabolism, and enters a state of waiting so prolonged that it almost escapes the ordinary definition of a fish's life. The lake may vanish from the surface, but its life is not over. It has not merely adapted to water, it has adapted to the possibility that water may one day disappear. Crocodiles, too, refuse to lock themselves into a single type of environment. Rivers can be home, lakes can be home, swamps can be home, estuaries can become corridors, feeding grounds, and places of refuge. Some species can even tolerate salt water for extended periods, expanding their range far beyond the familiar image of a freshwater predator. Yet a varied diet and flexible habitat are not the whole secret. Another quality appears again and again among these ancient survivors. They can endure conditions that many other species cannot. The history of Earth is not only a history of flourishing life, it is also a history of scarcity. Scarcity of food, scarcity of oxygen, shifting temperatures, rising and falling waters, habitats opening and closing. Many eras did not reward speed, power, or perfection. They rewarded endurance. Horseshoe crabs inhabit dynamic coastal zones where seawater and brackish water meet, where tides repeatedly transform sandbars into seabeds and then return them to the air. Lungfish can drastically reduce their metabolism and endure long droughts inside dark mud. Tuataras remain active at temperatures lower than those tolerated by most reptiles, as though their bodies have learned not to demand constant warmth from the world. Crocodiles can pass through long periods without food, remaining still, waiting patiently, spending less energy, never panicking in the face of scarcity. Their shared trait is not immortality. They remain vulnerable to countless changes and dangers. What sets them apart is that they do not build their entire future upon the assumption that conditions will always remain favorable. And here, one of evolution's great paradoxes begins to emerge. The longest surviving creatures are often not the strongest, not the fastest, not the smartest in the way humans usually imagine. They are often the ones with the most backup plans. When environments change, highly specialized species must wait for the world to return to its former shape. But the world rarely does. Flexible species can switch food sources, move into different habitats, alter their pace of life, retreat when necessary, slow down, or simply wait for difficult times to pass. Flexibility is not always spectacular. It does not create the dramatic image of overwhelming power. Yet across deep time, it possesses a quiet resilience all its own. Perfection often works only in a stable world, but Earth has never remained stable long enough for that reward to last forever. Mountains rise and wear away, seas advance and retreat. Climates spread forests and later turn them into dry landscapes. Food webs that once seemed permanent can fracture in what amounts to only a brief moment in the history of life. In evolution, perfection can sometimes resemble a beautiful room with only one door. Flexibility may be humbler, less impressive, less dramatic, but it leaves more ways out when the darkness arrives. This is the first rule revealed by crocodiles, horseshoe crabs, sharks, lungfish, tuataras, and sturgeons. The longest-lasting survivors do not necessarily endure by dominating everything around them. They endure because they never allow themselves to become completely trapped within a single way of life. But this is only the first rule. The more closely we examine these ancient survivors, the more another trait begins to emerge. It appears in sturgeons, in tuataras, in crocodiles, and in lungfish. They do not rush. They do not burn through everything in order to grow quickly, reproduce endlessly, and spend all their energy in a brief moment of success. They seem to operate according to a different clock, slower, but far more enduring. If the world suddenly became poorer one day, if food disappeared from the plains, the oceans, and the forests that had once been full of life for months or even years at a time, which creature would have a better chance of enduring one that must hunt every day to sustain a body constantly burning through energy, or one that can quietly wait until the difficult season passes? For most of life's ordinary history, the answer seems obvious. Moving faster usually means a better chance of escaping danger. Growing faster helps secure more resources. Reproducing earlier produces more descendants. Nearly every competition in nature appears to favor creatures that operate at high speed. Yet mass extinctions are not ordinary competitions. They do not simply take the lives of countless organisms. They break the connections that once kept the world functioning smoothly. Food chains unravel. Energy becomes scarce. Ecosystems that had endured for millions of years suddenly become fragile and unpredictable. Under those conditions, a high demand for energy is no longer an unquestionable advantage. It can become a burden. A strange pattern begins to emerge when we look back at the lineages that have survived the greatest crises in Earth's history. Many of them do not live at a frantic pace. They seem to give themselves more time. Crocodiles provide a clear example. Earlier, we encountered individuals capable of surviving for months after a single large meal. That ability is not a matter of luck. It comes from the way their bodies function. As cold-blooded animals, crocodiles do not constantly burn energy to maintain body temperature the way birds and mammals do. They allow the surrounding environment to perform much of that work. The result is a significantly lower energy demand. When food becomes scarce, they do not immediately enter a crisis. A period that many other animals would experience as a catastrophe may be little more than a waiting game for a crocodile. During times of chaos, a creature that spends less energy resembles a traveler carrying larger reserves on the same long journey. But crocodiles are not alone. On the islands scattered off the coast of New Zealand lives a creature that seems to experience time differently. The Tuatara is one of the slowest developing reptiles still living on Earth. It does not rush toward adulthood. Many individuals require close to a decade, or even longer, before reaching reproductive age. Its breeding cycle is slower than that of most modern reptiles. Its lifespan stretches across many decades, and even at an advanced age, it can continue reproducing. What is even more remarkable is the way its body operates. The Tuatara can remain active at temperatures that many other reptiles would struggle to tolerate. Its body temperature is often considerably lower than that of distant relatives living in warmer climates. That means nearly every process inside its body unfolds at a slower pace. It consumes less, requires less, and depends less on a constant flow of environmental energy. While many species must continually accelerate to remain competitive, the Tuatara seems to have chosen an entirely different rhythm. A rhythm so patient that it has become one of the last guardians of an ancient lineage. Yet there is another creature that takes this strategy even further. It does not merely live slowly, it can almost pause life itself. In many seasonal lakes and rivers across Africa, water can disappear completely during prolonged dry seasons. For most fish, that is a death sentence. Some must migrate, others perish when the water vanishes. The lungfish chooses another path. As the water retreats, it burrows deep into the mud below. Its body secretes mucus that hardens into a protective cocoon. Inside that temporary shelter, breathing slows, oxygen consumption decreases, heart activity diminishes. The entire metabolic system enters an extreme state of conservation. For months, and under certain conditions even longer, the lungfish can survive within a world that seems to have disappeared. When the water returns, it awakens and resumes life, as though it had simply taken a very long sleep. That moment reveals something worth reflecting upon. When its environment disappears, the lungfish does not attempt to move faster. It does the opposite. It slows life itself, looking across the animal kingdom as a whole. The same pattern appears again and again. In the cold waters of the North Atlantic and the Arctic, the Greenland shark grows so slowly that it almost defies belief. It may live for more than 3 centuries, and some estimates suggest lifespans approaching 400 years. Many individuals do not reach reproductive maturity until they have already lived for more than a century. This is not a life built on speed. It is a life built on endurance. Giant tortoises tell a similar story. They mature slowly, live for extraordinary lengths of time, and maintain low energy demands throughout much of their lives. Once again, longevity is not achieved by moving faster than everyone else. When we look back at the great extinction events, one truth becomes increasingly clear. These catastrophes rarely end in a single day. They often unfold through years of food shortages, years of environmental instability, and years of declining energy availability. During such periods, the ability to live slowly becomes an enormous evolutionary advantage. The more energy a creature consumes, the more dependent it becomes on the world's ability to provide resources without interruption. The less energy it requires, the more time it gains. Perhaps that is what this second rule is quietly telling us. During the most turbulent chapters of Earth's history, the winners are not always those that move the fastest. Sometimes, they are the ones that can keep going the longest. But living slowly is still not enough. Flexibility allows these creatures to adapt when circumstances change. A slower pace of life helps them endure harsh conditions. Yet as we continue following the trail left by the oldest survivors, another rule begins to emerge. They rarely place their future on a single path. They always leave themselves multiple possibilities for tomorrow. And that is the third thing. What is more dangerous for a living creature, a world that never stops changing, or knowing only one way to survive within it? The answer may sound simple, yet the hundreds of millions of years of life's history suggest that this is one of the most important questions ever asked. During long periods of stability, specialization is often a powerful advantage. A species finely tuned to a particular environment can exploit food more efficiently, compete more successfully, and expand more rapidly than a generalist. Over time, that success binds it ever more tightly to the world it has come to know. But Earth rarely keeps the same face for very long. Climates shift. Sea levels rise and fall. Ocean currents change course. Food webs are reorganized. Sometimes the entire planet enters vast biological crises. In moments like these, what was once a species' greatest strength can become its most dangerous weakness. When there is only one path to survival, the disappearance of that path means every option disappears with it. Creatures that preserve multiple ways of adapting, by contrast, often gain another chance to continue. Not because they are stronger, not because they are smarter. They simply do not depend entirely on a single promise from the future. Few lineages illustrate this better than sharks. They have existed longer than flowering plants, longer than modern birds, and longer than most groups of vertebrates alive today. When people think of sharks, they often picture a single kind of animal, a large predator cruising through the ocean. Reality is far more diverse. More than 500 shark species alive today follow remarkably different survival strategies. Some specialize in hunting large fish in open waters. Others focus on seals. Some search for squid in the depths. Others quietly forage along the seafloor. Some take advantage of carrion. Others, enormous in size, drift through the oceans with mouths wide open, filtering plankton from the water itself. From a distance, they are all called sharks. Look closer, however, and they become hundreds of different solutions to the same challenge of survival. If one food source declines, the entire lineage does not collapse with it. One branch may weaken, while others continue through their own strategies. A species may fail. The lineage still has other doors left open. The ability to maintain options extends beyond food. It also appears in where these animals live. The horseshoe crab offers a remarkable example. For hundreds of millions of years, it has persisted along coastal environments ranging from tidal flats to estuaries and coastal marshes. It can function in seawater, brackish water, and regions where salinity changes constantly with the seasons or the tides. That may seem ordinary when viewed over a single day, across millions of years. However, its significance becomes much clearer. Earth's coastlines have never remained still. Oceans repeatedly advance onto land and then retreat. Areas once submerged can become dry ground. Regions that were once stable can transform into bays and inlets. For a creature adapted to only one environmental condition, each of these changes can become a serious threat. For horseshoe crabs, they have often been little more than a familiar part of life. The same pattern appears again and again in many of the creatures we have already encountered. Crocodilians are not confined to a single type of habitat. Many species can live in rivers, lakes, swamps, estuaries, and even coastal brackish waters. If one environment becomes unfavorable, others remain available. Their ability to move among different ecosystems has helped this lineage endure changes that less flexible groups could not withstand. Lungfish take the idea a step further. When lakes begin to dry up, when oxygen levels in the water fall to dangerous lows, when their familiar environment nearly disappears, they do not remain completely dependent on water. They breathe with lungs, burrow deep into moist mud, and enter extended periods of dormancy. The outside world may become hostile, but they retain a backup plan. More than once, that backup plan has marked the boundary between survival and disappearance. This is also where one of evolution's great paradoxes begins to emerge. Many species vanished throughout history, not because they were weak. Quite the opposite. They were extraordinarily successful. They became highly efficient within a particular environment. They were optimized for specific conditions. They dominated the world they knew in remarkable detail. But when that world disappeared, the very advantages that had carried them to the top became anchors tying them to the past. The more dependent a species becomes on a single condition, the greater the risk when that condition vanishes. Research into the long-term persistence of biological populations often reveals the same recurring trend. Groups capable of adapting to a wide range of environmental changes generally have a higher chance of surviving than groups that rely too heavily on a single state of the world. After observing sharks, horseshoe crabs, crocodilians, and lungfish, a common pattern begins to come into focus. The longest-lasting creatures rarely place their entire future in a single food source. They do not place their entire future in a single habitat, nor do they place their entire future in a single strategy. Flexibility is not perfection. In fact, it often makes an organism less efficient in any one specific circumstance. Yet on a timescale measured in hundreds of millions of years, flexibility frequently proves more durable than perfection. The longest surviving lineages did not endure because they correctly predicted the future. No one can do that. They endured because they always left themselves more than one path forward when the future changed. By now, 3 rules have begun to emerge. Do not become too specialized. Do not live too fast. Always keep a backup plan. But then there came a moment in Earth's history when all 3 of those rules faced their greatest test. 66 million years ago, a massive celestial body slammed into the Yucatan Peninsula. In that instant, the world was forced to make its final choice. Who would remain, and who would disappear forever? If you could travel back to Earth just one day before one of the most famous events in the history of life, the outcome would seem obvious. Across vast plains, enormous herds of plant-eating dinosaurs moved like living tides. In forests and open landscapes, predators such as Tyrannosaurus occupied a position no other creature dared challenge. They possessed size, power, and dominance built through more than 160 million years of evolution. Around 66 million years ago, near the end of the Cretaceous period, most land ecosystems revolved around the presence of dinosaurs. Mammals were still largely small creatures that lived in the shadows or beneath low vegetation. Crocodilians rested quietly in swamps. Turtles moved slowly between bodies of water. Many ancient lineages seemed to survive only in overlooked corners of the world. Every sign pointed towards the same conclusion. The dinosaurs were the winners. Yet only a few hours later, the history of life changed direction. The force behind that turning point was not a war between species. It was not the arrival of a new predator. It was not competition unfolding over generations. Its origin came from beyond Earth. A celestial object, roughly 10 to 15 kilometers wide, hurtled toward the planet at tremendous speed. The impact site lay near what is now the Yucatan Peninsula. Its size can be imagined as an entire mountain falling from the sky. The collision released an amount of energy beyond anything humans have ever witnessed in recorded history. The ground shook violently. A gigantic crater formed, molten rock and material from Earth's crust were blasted high into the atmosphere. But the most dangerous consequences did not end at the point of impact. Glowing debris returned to the surface as prolonged storms of fire. Vast forests ignited. The sky burned with immense heat. Soon afterward, billions of tons of dust, ash, and fine particles were pushed into the upper atmosphere. Forming a planetary veil, sunlight dropped dramatically. Forests that depended on photosynthesis began to weaken. Plant life declined. Herbivores lost their food supply. Predators that depended on them gradually lost theirs as well. A chain reaction spread from land to sea, from the tropics to the poles. The collapse did not happen because one species was stronger than another. It happened because the foundation supporting entire ecosystems was suddenly pulled away. What makes this event especially remarkable is that the asteroid did not directly decide who would disappear. It merely created new conditions. The biological traits of each group ultimately determined whether they could survive the crisis. The most visible victims were the creatures that had once stood at the top of the world. The non-avian dinosaurs that had dominated nearly every terrestrial ecosystem vanished from the record of life. From gigantic predators to immense herds of plant eaters, none survived the catastrophe. In the skies, the flying reptiles that had ruled the air for tens of millions of years disappeared as well. In the oceans, many giant marine reptiles that occupied the highest levels of the food chain, including mosasaurs and plesiosaurs, were gone after the event. A paradox began to emerge. The creatures that had held the greatest power often became the most vulnerable once the energy sustaining the entire ecosystem suddenly disappeared. Meanwhile, in places few paid attention to, some ancient lineages endured. Crocodilians provide a clear example. They do not require the constant energy intake demanded by large, highly active animals. Their low metabolic rate allows them to survive long periods without food. When many creatures were pushed beyond their limits, those seemingly slow and unremarkable traits became advantages. Turtles also belonged to the ranks of survivors. Many species were closely tied to aquatic environments, where some of the direct effects of the disaster were softened. Their ability to endure harsh conditions, combined with relatively modest energy demands, helped them persist. Perhaps the most fascinating story belongs to the birds. The dinosaurs did not disappear completely. A small branch of that great family survived. Those feathered creatures endured the catastrophe and eventually became the ancestors of modern birds. Every birdsong heard today is a reminder that part of the dinosaur dynasty is still present around us. Small mammals also made it through the crisis. Their size meant lower energy requirements. They could shelter in burrows, consume a wide variety of foods, and maintain populations on far fewer resources than giant animals. Once the worst had passed, those creatures that had once lived at the margins became the pioneers of a new age of mammals. When the survivors are placed beside those that vanished, a familiar pattern becomes increasingly clear. Dominant animals often require more food, more space, and more stable ecosystems to sustain their existence. When the world functions normally, these requirements are advantages. When the world changes suddenly, they become burdens. By contrast, creatures capable of eating a wider variety of foods, enduring hunger for longer periods, adapting more readily, and avoiding complete dependence on a single condition, tend to have a greater chance of survival. The three principles that have appeared again and again throughout the journey of the survivors were once more confirmed. Do not become too specialized. Do not live too fast. Do not place your future in a single option. An asteroid became the harshest test those principles would ever face. The day it struck was not the day life failed. It was the day the balance of evolution changed hands. The dinosaurs did not disappear because they were weak. They disappeared because the world changed faster than the ecosystems they depended on could adapt. Meanwhile, smaller and less celebrated creatures happened to carry traits better suited for an age of crisis. Survival is not always victory. Sometimes it is simply the ability to endure longer than those who were stronger. The history of life is not always written by the dominant creatures. More often, it is written by those that remain after the final storm has passed. Yet the journey is not over. Crocodilians survived. Horseshoe crabs survived. Sharks, lungfish, tuataras, and sturgeons survived as well. They endured asteroid impacts. They endured supervolcanoes. They endured mass extinctions that erased most life on the planet. Today, however, many of those ancient lineages face a very different challenge. A challenge that does not come from space. Not from deep within the Earth. Not from the natural changes of the planet itself. It comes from a species that appeared only very recently in Earth's history. Humans. What could be more dangerous than an asteroid 10 kilometers wide? It sounds like an impossible question. Throughout Earth's history, rocks falling from space have been powerful enough to reshape the fate of an entire planet. They erased vast ecosystems and wiped out countless lineages that had dominated the world for tens of millions of years. Yet in the 21st century, a different paradox is beginning to emerge. Many creatures that survived asteroid impacts, supervolcanoes, and some of the greatest mass extinctions in history are now starting to decline. What makes this reality so thought-provoking is not simply the change itself. In the distant past, many environmental upheavals unfolded over thousands or even tens of thousands of years. On a geological timescale, those events were still astonishingly rapid, yet they often left enough time for populations to migrate, adapt, or rely on survival strategies shaped by millions of years of evolution. Today, many changes unfold within just a few decades. Some ecosystems are shifting far faster than the familiar pace at which ancient lineages have lived for countless generations. Perhaps the most frightening thing is not always the size of a catastrophe. Sometimes it is the speed of change. Throughout this journey, we have encountered animals that witnessed the collapse of ancient worlds. They crossed extinction boundaries that countless other species failed to survive. Yet today, many of those same names are appearing with increasing frequency on lists of threatened species. One of them is the shark. More than 400 million years ago, long before the first forests covered the land, the ancestors of sharks were already swimming through Earth's primordial oceans. They survived all 5 major mass extinctions. They adapted to icy seas, tropical waters, shallow coastlines, and deep ocean trenches where sunlight never reaches. Their diversity of hunting strategies and their presence across nearly every ocean helped make sharks one of the most successful lineages in the history of life. But the modern age has brought pressures unlike anything they faced before. Commercial fishing, overexploitation of marine resources, accidental bycatch, declining prey populations, and demand for shark products have driven severe declines in many populations. The irony is that some of the very traits that helped sharks remain stable over immense stretches of time now make recovery more difficult. Many species mature slowly, produce relatively few offspring, and reproduce over long cycles. Once their numbers fall, rebuilding populations takes far longer than it does for rapidly reproducing species. A group of animals that swam through 5 planetary mass extinctions now faces a challenge created within only a few centuries of human activity. And sharks are not alone. In the ancient rivers of the Northern Hemisphere, another lineage faces a similar paradox. Sturgeons are among the oldest surviving groups of fish on Earth. They can live for extraordinary lengths of time, migrate through multiple ecosystems, and maintain life cycles that stretch far beyond the lifespan of many human civilizations. Their survival strategy has always been tied to long, uninterrupted rivers. They need open migration routes. They depend on spawning grounds passed down across generations. For millions of years, that system worked remarkably well, allowing the lineage to endure countless geological and climatic changes. But in the modern world, dams now stand across many rivers. Water flows have been altered. Migration pathways have been fragmented. Many traditional spawning areas can no longer be reached. The continuing demand for caviar has placed additional pressure on populations that were already struggling. Today, every surviving species of sturgeon and paddlefish belongs to a threatened category of some kind. Several have moved dangerously close to extinction. The strategy that carried sturgeons through hundreds of millions of years simply was not built to cope with artificial barriers that appeared within a few decades. Yet perhaps the greatest paradox belongs to a creature that humans both protect and exploit. Horseshoe crabs have existed since a time so distant that many of today's continents had not yet taken their modern shape. Inside their bodies flows a remarkable blue blood. Cells within that blood react with extraordinary sensitivity to bacterial toxins. Because of this unique property, horseshoe crabs have played a critical role in testing the safety of vaccines, injectable medicines, and numerous biomedical products. Yet that same value comes with another side. Every year, hundreds of thousands of horseshoe crabs are collected for biomedical breeding programs. Some do not survive. Others experience reduced activity levels or diminished reproductive success afterward. The effects extend beyond the crabs themselves. Their eggs provide an essential food source for many migratory shorebirds. As horseshoe crab populations decline, other links within the ecological network begin to feel the consequences as well. A creature that survived hundreds of millions of years of Earth's history has now become a resource within modern civilization. Far to the south, on islands scattered off the coast of New Zealand, another familiar survivor faces challenges its ancestors never encountered. The Tuatara is the final surviving member of an evolutionary branch that was once rich and diverse. It tolerates cold conditions well. It lives slowly. It has changed remarkably little through time. Those traits helped it endure, while many relatives vanished. But the ancient ecosystem in which the Tuatara evolved never had to contend with rats, cats, or other introduced predators. These new hunters appeared far too quickly for the Tuatara to develop corresponding defenses, Another pressure works more quietly. The sex of a Tuatara hatchling is influenced by the temperature at which the egg develops. As temperatures rise, the proportion of males also increases. If that trend continues, the balance between sexes may become distorted, creating long-term consequences for the survival of entire populations. A species that existed before dinosaurs rose to dominate the land now survives only within carefully protected areas. When we step back and look at all of these stories together, one important difference begins to emerge. During ancient mass extinctions, asteroids did not choose their targets. Volcanoes did not choose their targets. Climate shifts did not choose their targets. Every organism faced the challenges of its era. Today, many pressures are concentrated directly on the places that matter most to each species. The rivers where sturgeons spawn, the seas where sharks hunt, the nesting beaches of horseshoe crabs, the last islands where tuataras endure. Creatures that once witnessed the disappearance of dinosaurs now face an entirely new opponent, a single species, humans. That does not mean their story has reached its end, but it does remind us of something important. A history of survival is not a guarantee of the future. No species is immune to change. Every era creates its own challenges, different from anything that came before. Life is never secured by victories of the past. Every generation, every lineage, and every ecosystem must face the test of its own time. They survived asteroids. They survived supervolcanoes. They survived periods when life on Earth came close to being erased. But if so many species are disappearing today, if rates of decline continue to accelerate across the world, a new question begins to emerge. Are we witnessing the opening chapters of an event that the future may one day call by a familiar name, the sixth mass extinction? Across more than 540 million years of complex animal life, Earth has repeatedly witnessed moments when life seemed to be pushed to the edge of collapse. The end of the Ordovician, the end of the Devonian, the Permian mass extinction, the end of the Triassic, the end of the Cretaceous. 5 times. Ecosystems that had remained stable for tens of millions of years were shattered. 5 times. A vast portion of the planet's species disappeared. When we look back at those periods, it is easy to think of them as completed chapters of history, events buried deep in the past and visible only from the safe distance of hundreds of millions of years. Yet there is another question that is asked far less often. If a new mass extinction were beginning right now, would we recognize it while living through it? Or would it take observers millions of years in the future to stand far enough away to see the full picture? No creature living at the end of the Cretaceous knew it was witnessing the final days of the age of dinosaurs. Life continued from one day to the next. Ecosystems still functioned. Food webs remained intact. Only when viewed from the future did the boundary between two worlds become clear. Throughout this journey, we have met survivors, crocodiles, sharks, lungfish, horseshoe crabs, tuataras, creatures that endured the greatest crises in the history of life. But before we can truly understand the value of survival, we must first understand what now threatens the web of life itself. When people think about mass extinctions of the past, they often imagine giant asteroids or volcanic eruptions, so immense they almost defy imagination. An asteroid striking the Yucatan Peninsula helped bring down food chains across the globe. Massive eruptions in Siberia released extraordinary amounts of gas into the atmosphere, altering living conditions on a planetary scale. Yet most organisms did not die directly from the asteroid or the lava. The greater danger came afterward. Temperatures changed too quickly. The oceans lost their chemical balance. Large regions of the sea became depleted of oxygen. Food webs began to unravel. Species that depended on one another could no longer find the conditions necessary to survive. A mass extinction is not a single explosion. It is more like a chain reaction that unfolds across generations. When one link disappears, the next begins to weaken. When environments change too quickly, the ability of many species to adapt can no longer keep pace. What concerns many researchers is that some of those familiar warning signs are appearing once again. This time, they are not arriving from space. Their source is the activity of a single species, humans. Across the planet, habitats are increasingly being broken into smaller and smaller fragments. Tropical forests that were once connected are now divided by roads, cities, and agricultural land. Wetlands, grasslands, mangrove forests, and coral reefs are losing much of the space they once occupied. Animal populations that once moved freely across vast landscapes now find themselves isolated within biological islands. That isolation does more than reduce numbers. It decreases genetic diversity. It weakens resilience against disease and environmental change. It increases the risk of local extinction. Alongside habitat loss comes exploitation, industrial fishing, illegal hunting, logging, marine extraction, and wildlife trade are placing pressure on countless populations at the same time. In nature, many species can recover from periods of decline. But when losses occur faster than reproduction, that recovery mechanism begins to fail. The climate is also changing at an accelerating pace. Global temperatures continue to rise. Heat waves are becoming more frequent. Melting ice is reshaping natural systems that remained relatively stable for long periods. Sea levels are shifting. Climate zones are gradually moving across the planet. Many species that once adapted to changes unfolding over thousands of years are now confronting transformations that occur within only a few decades. Then there is the spread of invasive species through trade, transportation, and other human activities. Organisms are being carried into regions where they have never existed before. Some become new competitors, some become new predators. Others bring unfamiliar diseases. On islands especially, these impacts are often far more severe than those seen on large continental land masses. Each of these pressures alone would be significant. What draws even greater attention from scientists is that they are happening simultaneously. When we look back at the 5 great mass extinctions of the past, a familiar pattern emerges. The environment changes too quickly. Ecosystems lose stability. Food webs break apart. Many species run out of time to adapt. Today, habitats are shrinking. Oceans are changing. Temperatures are rising. Species are disappearing at rates significantly higher than the natural background extinction rates that characterized most of geological history. Yet one enormous difference remains. Previous mass extinctions had no conscious agent behind them. This time, one species is influencing nearly every ecosystem on Earth: humans. Whether these changes are already sufficient to define a sixth mass extinction remains a matter of debate. Many researchers argue that current extinction rates are unusually high, that numerous biological indicators are declining simultaneously, and that the planet may already have entered the early stages of a new mass extinction event. Others are more cautious. From their perspective, mass extinction is an immense geological concept that requires far longer periods of time before it can be fully confirmed. Regardless of where they stand, most agree on one central reality. Global biodiversity is declining at an alarming rate. The pace of change we are witnessing today has no precedent in the entire history of human civilization. The numbers help bring that picture into focus. More than 47,000 species are currently classified as threatened with extinction. Roughly 1 million species may face extinction in the coming decades if present trends continue. The average size of monitored wildlife populations worldwide has fallen dramatically since the 1970s. These numbers are not signs of a final ending. They are more like warning signals from a system under increasing strain. If a paleontologist were to appear 10 million years after us, they might know nothing about the nations that once existed, nothing about the wars that were fought, nothing about the languages that were spoken. But within sediment layers and fossil records, they might see something unmistakable. A period during which an extraordinary number of species disappeared within a relatively short span of time. A mass extinction does not begin with complete silence. More often, it begins with changes so small they are easy to overlook. A forest is fragmented, a river is blocked, a breeding ground disappears, one population declines, then another. The history of life is rarely written through sudden endings. It is written through countless small changes accumulating over time until they become large enough to define a new age. If life has repeatedly approached the edge and returned, if sharks, crocodiles, lungfish, horseshoe crabs, and tuataras have survived moments when the world itself seemed to be ending, then after everything we have seen, what is the greatest lesson these last survivors leave behind? (8.15) The Last Survivors. If we stood on a shoreline of Earth around 450 million years ago, among the wet mudflats at the edge of a world still strange and unfamiliar, we might have seen creatures resembling horseshoe crabs slowly moving across the shallows. At that time, forests had not yet spread across the land. The sounds of large animals did not yet exist. Life was still experimenting with its first tentative steps on a young planet. If we moved forward to a river more than 200 million years ago, the earliest ancestors of crocodiles had already appeared. They lived in a world where dinosaurs were just beginning their rise. Millions of years later, after most of those giants had vanished, the crocodile lineage remained. Travel farther still to the isolated islands off the coast of New Zealand, and we would encounter the Tuatara, a creature that seems almost detached from the present, the last surviving representative of an entire evolutionary branch that once spread across large parts of the ancient world. What connects all of these animals? What allowed them to outlast countless species that once ruled the planet during the height of their glory? To answer that question, the entire journey we have taken must now be viewed as a single picture. Each creature is no longer a separate story. They become pieces of a puzzle slowly fitting together. The horseshoe crab is one of the oldest living witnesses to the history of complex life. Its lineage can be traced back nearly 500 million years, long before the first forests covered the continents. Its ancestors already inhabited shallow seas. Long before the first dinosaurs appeared, they had existed for ages. What makes them remarkable is not their strength or size. What makes them remarkable is that their lineage passed through all 5 of the greatest mass extinctions known to science. Then there are the crocodiles, the keepers of the swamps of time. More than 200 million years ago, their ancestors emerged within ancient ecosystems. They witnessed the rise of the dinosaurs. They witnessed the fall of the dinosaurs. Throughout that immense span of time, their secret was never exceptional speed or unmatched aggression. Their secret was patience, a body designed to conserve energy, a lifestyle built around taking advantage of opportunities whenever they appeared. But not every survivor chose to stand still. Sharks followed a path that was almost the opposite. Many people assume they endured because they never changed. The reality suggests the reverse. Across hundreds of millions of years, shark lineages continuously produced new forms of life. Some became apex predators. Some survived by scavenging. Some searched for prey along the seafloor. Others evolved into gentle giants that filtered plankton from seawater. The success of sharks was never based on a single formula. Their success came from constantly creating many different ones. Meanwhile, lungfish represent an entirely different strategy. When shallow waters gradually disappeared, many organisms were forced into a struggle for survival. Lungfish chose a quieter path. They burrowed into mud, secreted a protective cocoon, slowed almost every bodily function, and waited. Instead of trying to defeat the environment, they waited for the environment to change. Then, there is the Tuatara, the final guardian of an ancient dynasty. Around 250 million years ago, its evolutionary branch separated from the common ancestor it shared with lizards and snakes. In the distant past, that lineage was highly diverse. Time slowly narrowed its world until only a single representative remained. The Tuatara is not evidence of dominance. It is evidence of life's extraordinary endurance. When all of these creatures are placed side by side, a paradox begins to emerge. None of them were the fastest animals of their age. Crocodiles live slowly. Lungfish live slowly. Tuataras grow so slowly that some stages of their lives stretch across decades. None of them were the strongest. History has seen countless predators that were larger, more aggressive, and more terrifying. Most of them disappeared. None of them were the most numerous. Many ancient populations survived in relatively small numbers within limited environments. None of them conquered the planet through intelligence. If evolution were a competition designed to produce the perfect organism, many of them should have been eliminated long ago, yet they are still here. So what truly connects them? The answer begins to appear through the qualities that repeat from one creature to another. The first is flexibility. Sharks evolved many different feeding strategies. Crocodiles can survive in a variety of aquatic environments. Horseshoe crabs tolerate dramatic changes in salinity. Lungfish shift between different states of living depending on surrounding conditions. They do not place their entire future on a single set of circumstances. The second is patience. Crocodiles can endure long periods without food. Lungfish can wait through severe dry seasons. Tuataras grow according to their own slow rhythm. They possess a rare ability in the natural world, the ability to keep existing while waiting for a better time. Then comes efficiency. Many ancient creatures maintain low metabolic rates, low energy demands, and long lifespans. They do not need to win every day. They only need to survive today in order to reach tomorrow. And finally, resilience. None of them place all their hopes in a single food source, a single habitat, or a single survival strategy. When one path closes, another remains. Looking back across more than 500 million years of planetary history, Earth has witnessed countless biological empires rise and fall. Giant creatures once dominated the land. Entire ecosystems once appeared invincible. Great lineages once seemed destined to last forever. In the end, time took almost all of them away. What remains are not those who always won. What remains are those who could continue when winning no longer mattered. Horseshoe crabs have seen worlds that no mammal has ever known. The Tuatara is the final echo of a vanished biological dynasty. Lungfish still carry within their bodies traces of the age when vertebrates first began experimenting with life beyond the water. All of this points toward a simple conclusion. Evolution is not a contest to find the perfect organism. It is a series of experiments stretching across hundreds of millions of years, where every time the world changes, the same question is asked again. Who can adapt? Who can wait? Who can continue? The longest surviving creatures in history are not the ones that won every battle. They are the ones that endured long enough to watch every other winner disappear.